In this video, I'm going to talk about the basics of calibration, and in the next section we'll get into a little bit more detail about each of the different calibration methods. So when we are calibrating a method, we could also call it standardizing a method. So this is the process of determining the relationship between the signal and the amount of analyte in the sample. So if you think about some of the experiments you have done in lab or will do in lab, for example, the copper EDTA, the flame photometer experiment, or the iron vitamin experiment, what you are doing is measuring absorbances or emissions, but the instrument, it doesn't know what the concentration is. It doesn't know that a specific absorbance equals a specific concentration. So when you're calibrating or standardizing a method, what you're doing is trying to figure out how the concentration of a specific sample relates to the signal. So this concentration gives this particular signal, another higher concentration gives a higher signal, etc. So to standardize a method, you must use standards of known concentration. Hopefully that's obvious, because you have to know what the concentration of the standard is in order to relate it to the signal that your instrumentation is giving. And the quality of the standardization depends on the quality of the reagents and glassware used for the standardization. So you need to use pure reagents and glassware that is accurate. So when you're making standards of known concentration, you have to consider a couple of things. And what you really need to use is something called a primary standard. So a primary standard is a reagent that we can dispense an accurate amount of analyte, usually by mass, and it must meet the following criteria. So number one, it has to have a known stoichiometry. So we have to know, for example, when this is dissolved in water, how it breaks up. It has to have a known purity, usually 99.9% pure or better. And the reason for this is if it is, for example, 80% pure, it's not 80% pure by mass, it's 80% pure by composition. So we might know that 80% of the composition is, for example, KHP, and we know how much that weighs in terms of its mass per mole, but the impurities, we don't know what they are, and we also don't know how much they weigh. So they could weigh a little bit more or a little bit less than the KHP, or a lot more or a lot less. So we don't know exactly how much KHP would be in there if it wasn't as close to 100% pure as we possibly can get it. So that's why in lab the KHP is essentially 100% pure. A primary standard has to be stable for long-term storage, and it also has to be stable when dried. So the KHP, we dried that in an oven. That allowed any moisture to be removed from the KHP. So you're not weighing the water as well as the KHP. Any mass that you weigh is only going to be KHP. And some examples of primary standards besides KHP are sodium carbonate and potassium dichromate. Now, standards that are not primary standards are called secondary standards. And an example of a secondary standard is sodium hydroxide. So when you prepare sodium hydroxide, we can't just weigh out pellets of sodium hydroxide and dissolve that in a known amount of water to determine the concentration of sodium hydroxide. And the reason we can't do this is because sodium hydroxide is impure, at least the one that we use in lab, and it's also what's called hygroscopic, which means it can adsorb moisture from the air really easily. So as soon as you expose the pellets to the atmosphere, it'll be adsorbing some water, which means that the mass of sodium hydroxide will be continuously changing as you're trying to weigh it. So that's not going to be good for determining how much sodium hydroxide is there when the mass is continuously increasing. Okay, so the concentration of a secondary standard has to be determined relative to a primary standard, and that's exactly what you did with the KHP lab, and then again in the macrosodium lab if you've done that one as well. So standards don't always just contain water and the analyte. So for the KHP, you had KHP and water. For the copper lab, it's copper and water. But for the iron vitamin lab, there are a few other reagents that have to be added to the iron solutions in order to make the reaction occur to turn the solutions the desired color. So the impurities in these reagents could affect your result. So for example, if the orthophenanthroline in the iron vitamin lab contained some iron, that's going to be a problem because you're trying to measure iron in your sample. So if the reagents themselves contain the analyte, then your signal is going to be dependent at least a little bit based on that particular reagent. So we usually look for reagent purities that are called either reagent grade or ACS grade. Those are just common grades of reagents that have low amounts of impurities and are suitable for most lab uses. But let's just take something really simple, because this is the solvent that we use in all of our labs, and that is water. So there are actually a number of different grades in water. In the lab, we have essentially three: tap water, distilled water, and deionized water. Tap water contains a lot of sodium, a lot of calcium, a lot of magnesium, and a lot of other ions and compounds within it that make it safe for us to drink. Distilled water removes some of those impurities, but not all of them. And then deionized water takes the distilled water through a column, which then removes more of the ions. So takes away the sodium, takes away the potassium, takes away the calcium, takes away the magnesium, and so on. So in lab, notice that we don't always use deionized water, and we don't always use the reverse osmosis water, which is essentially distilled water. And we have to be smart about which water we use, because water, depending on its purity, can have vastly different prices. And here's some examples at the bottom of this slide. So if we just got 4 liters of water from Meyer, it's $1, maybe $2, maybe $5. Whatever it is, it's pretty cheap. Now, if we're doing an experiment that requires much more pure water, such as HPLC, which stands for high performance liquid chromatography, you'll learn about this in Chem 383 or 481 if you take those courses later on. 4 liters of that water costs about $110. And if we want to get even more pure, something for liquid chromatography with mass spectrometry, that same water is going to cost $250. This is just for a gallon, right? About 4 liters. So the price of that water depends on the purity, and the purity is guaranteed based on many different analyses, many different purification processes that make sure that that water does not have anything at any concentration that can be detected by a specific method. So for example, the $250 water has to have really, really, really low concentrations of everything in it, because mass spectrometry can measure extremely low concentrations of things. We're talking less than part per billion. So that's why it's so expensive. And that's why we have to be careful about what kind of water we choose. If we choose to use tap water or reverse osmosis water for the macro sodium lab, that's still going to have sodium in it, and you are trying to determine a sodium concentration in that particular lab. So using deionized water, make sure that there's no sodium in the water itself. So the only sodium that you are going to be measuring is from your unknown. So the other thing to consider when preparing standard solutions, again, a standard solution, we need to know what the concentration is, as exact as we can. So what kind of glassware do we use? Do we use beakers? Do we use volumetric flasks, Erlenmeyer flasks, pipettes? If we want to be certain of our concentration, we're going to have to use higher quality glassware. If you notice on a beaker, it does have little graduations that tell you what the volume is. But what I will say is that that is approximate. And another way to look at it is, let's just compare it to a volumetric flask. So you've all used one of those, and it has a line on it that you fill it up, the meniscus up to, so the bottom of the meniscus is just touching that line. If you do the same thing with a beaker, well, first of all, the beaker is much wider, so it's harder to see a meniscus, but you can just get the water level up to, say, 100 milliliters, just like a 100 milliliter volumetric flask. So let's just say you've done that. Now add a drop of water to each of those containers. In the volumetric flask, you will notice that the 1 drop of water has increased the volume to a point where it's above that line. So you definitely know that it's more than 100 milliliters. If you do the same thing in a beaker, even if that line was exactly at 100 milliliters, 1 drop is not going to make any difference in how you read that volume. So a beaker is extremely inaccurate. A volumetric flask, much more accurate. So when transferring volumes from one container to another, if you want to be accurate, you have to use a pipette for the same reason that you use a volumetric flask to contain very specific volumes of liquid. The pipette has a very narrow neck on it, so it's easy to see where the meniscus hits the little line on the pipette, and you know very easily if you are away from that line or delivering a different volume. A volume that you wouldn't know exactly because a pipette that you use in lab is calibrated specifically to deliver the 1 milliliter, 2 milliliter, 25 milliliter, 50 milliliters, right? You can't deliver 27.5 milliliters from a 50 milliliter volumetric pipette, right? It's not meant to do that. Okay, so once you've figured out what reagents you want to use, you've figured out what glassware you want to use, now you got to determine how are you going to prepare these samples. To do that, you need to know over which concentration range that you're going to prepare. So is it going to be a narrow range, say from 1 ppm to 10 ppm, or is it going to be a really wide range, say 1 part per million to 1,000 parts per million, basically 1 part per 1,000, right? So we have a much wider range in the second example than we do in the first example. So in one example, we might be fine just using 100 ppm standard solution, removing 1 milliliter, transferring that to a 100 milliliter volumetric flask to make 1 ppm, and then 2 milliliters from the 100 ppm to another volumetric flask to make 2 ppm, and then 3 ppm and 4 ppm made the same way. That's pretty easy because we have a very narrow range of concentrations that we're trying to prepare. But if we're trying to prepare a very wide range of concentrations, then that's when we use serial dilution. So that's when we would prepare one sample from our original stock solution. So let's say our original stock solution was 10,000 part per million or 10 part per thousand. So if we want to prepare the first dilution, which is to a 1,000 ppm or 1 part per thousand, we would dilute the 10 part per thousand sample or stock solution by a factor of 10 to get to the 1 part per thousand. And then using the 1 part per thousand solution that we just prepared, dilute that by a factor of 10 to make the 100 part per million, and then dilute using the 100 part per million, dilute that by a factor of 10 to make 10 part per million, and then using 10 part per million, use that sample, dilute that by a factor of 10 to make the 1 part per million solution. So each of these dilutions in a serial dilution is happening in a different flask, but since we are using the standard that we just prepared to make the next one, we can easily make a wide range of concentrations because we can dilute them all, say, by a factor of 10. So instead of using a 10 milliliter pipette, then a 1 milliliter pipette, then a 0.1 milliliter pipette, then a 0.01 milliliter pipette, which we may or may not have in the lab, using a serial dilution makes it much easier, and we can also use larger volumes, which are prone to less error than smaller volumes. So we've already talked a bit about sensitivity a few chapters ago, and we know that sensitivity is the ability of a method to distinguish the difference between samples of different amounts of analyte. So we can determine the sensitivity using a single point, for example, using this point on the curve, but that's not ideal because we don't know the shape of the calibration curve or the shape of this line and over what part of the concentration range being down here, we don't know over which range it is linear, and that's going to become important as we'll talk about in the next section. So it's better to use a multi-point calibration. So in that case, we might say use 3 points. So if we chose those 3 points there, we can see those are on a straight line. And we can figure out a slope of the straight line. We can figure out the sensitivity, because remember, sensitivity is the slope. But if we continued on, we might notice that this continues straight, but we also might notice that it curves. So this might be the actual relationship. So if we were to choose a 1-point standardization, and instead of using one of the red points, we end up using one of the blue points, notice how the slope is going to be quite a bit different for both the blue line and the red line. So it's important to use more than 1 point when doing a calibration or when determining sensitivity or when determining the slope of your calibration curve, because you need to know the shape of that curve and when it starts to deviate from linearity. So we'll talk a little bit about more what this external standard method is in the next section. But basically what it means that the analyte is being put in each of the standards from a stock solution, and that's the only source of analyte. There is another method that we'll talk about also called the standard addition method, where some of the analyte in each standard is actually from the sample. Now, one last thing that you have to consider when making your standards for an analysis is that the matrix of the standards should match as closely as possible to the matrix of the sample that you're analyzing. Now, in lab, that's fairly simple because the matrix is water. Matrix just means what is the sample in? Is it in river water? That just means that the matrix is river water. Is it in a crude oil sample? So the matrix would be the crude oil. Is it in soil? The matrix would be soil. So the matrix can be complicated, and especially if we're working with environmental samples, it will be complicated. And it's very difficult to replicate that complexity in the lab. So even something that you might think is simple, like river water, you think, well, we could replicate that in the lab, couldn't we? It's just mostly water. Yes, it is, but there's also a whole bunch of different elements in there. There's pretty much every element on the periodic table can be present in a natural water sample. It can have lots of organic material. It could have minerals. And how would you know what's in a river water sample without actually doing an analysis? And if you've already done the analysis, then what's the point of preparing a sample or a standard that has that particular matrix? You already know what's in there. All right, so usually the matrix isn't clean, not like in lab where it's just water. So the consequence of that is the matrix itself could have an effect on the signal that you're getting from your analyte. So under normal circumstances, maybe you get this red line here. So this would be an external standard method where you would prepare your standards in a relatively clean matrix. So water, for example, if our sample is from river water. Now, if we ran an analysis of our sample, so here is our sample, the signal of the sample, and it gave us a signal represented by the blue line here. If we were to extrapolate that to our calibration curve and to determine what the concentration is, then we would get a concentration of Ca, whatever that is. But since the river water is a complex matrix, maybe there's something in there that suppresses the signal. So instead, we're getting the black line as a calibration curve, or that's what it should be if we had river water as the matrix. So now notice that if we had the same sample signal, when we extrapolate that over to the curve, then we get a much different concentration. That's a higher concentration. So there's quite a bit of difference, or we can assume there's quite a bit of difference between those two concentrations. So just by making our standards in a clean matrix versus something much more closely related to the matrix of the sample could have a large effect on the concentrations that we are measuring. And as an analytical chemist, we want to be as accurate as we can when determining the concentration of our analyte in whatever matrix it is, because we've probably been hired to do that, and depending on the concentrations that we get, those might have certain implications for a company, for a government, or whoever else hired us to make that determination. So we have to be as accurate as possible, so we try to take into account every potential variable that we can. Right? So again, just to summarize some of the things we have to take into account, we have to take into account the matrix, we have to take into account the glassware that we're using, we have to take into account the other reagents that are going into our standards, right? They have to be as pure as possible. Okay, so this was the overview of calibration. In the next section, we'll get more into the nitty-gritty of external calibration, standard addition method, and another method that I didn't talk about called the internal standard method. Now, most of this is described I think in pretty good detail on the worksheets, so I'm going to use those and you can follow along with me. And as usual, if you have any questions, let me know and I'll be happy to help.